Swayam Prabha. Digital India. Educated India.
Welcome to the lecture number 29. Let us continue our discussion on fluorescence anisotropy, and till date what we have done is to find out what will be the time dependence of the intensity of fluorescence when collected in the parallel direction. That means, I parallel as a function of t, that we have seen in the last class. Let us write it once again. So, what we have seen that I parallel t is equal to I 0 by 3 e to the power minus t by tau f into 1 plus twice r 0 e to the power minus t by tau over. Similarly, we can also calculate that the same procedure can be used to evaluate the I perpendicular t, and if you do so, I will just write two steps over here. You will get I 0 by 3 e to the power minus t by tau f, and immediately you will get 1 plus 3 I y 0 minus I x 0 minus I y 0 minus I z 0 divided by I 0 e to the power minus t by tau over. So, this is I 0 by 3 e to the power minus t by tau f. From here it will be minus. So, into 1 minus r 0 e to the power minus t by tau over. Good. So, what I got two equations, one is for I parallel t and another is for I perpendicular t. Now, I can immediately write the form of R t, right. This is my anisotropy, which is also time dependent. So, for this R t, what I will do? I will put this expression for this I parallel t minus I perpendicular t divided by I parallel plus twice I perpendicular. In this case, I am taking the g value equal to 1, but if there is any g value I can take, but the form, right, will be like this only. Right. Okay. Now, let me write this two form. So, here will be my I 0 by 3 e to the power minus t by tau f 1 plus 2 r 0 e to the power minus t by tau over minus, this is I parallel and minus I perpendicular. So, I 0 by 3 e to the power minus t by tau f 1 minus r 0 e to the power minus t by tau over divided by this is straightforward, nothing special. Just you have to substitute this expression for I parallel and I perpendicular, and you just need to solve it, simplify it. And this looks big, but if you simplify, and which you can do later, what you will going to see is a very simple form of this, which is nothing but r 0 into e to the power minus t by tau over. So, you see this simplification right, I will get like this way. So, ultimately what I got, R t is R 0 e to the power minus t by tau r. That means, the value of r will start from R 0, and when the t is very large, eventually the value of r will going to be equal to 0. So, the value of r, which is anisotropy, will start from R 0 and will decay to 0, and that decay will be exponential in nature. See here, I have this e to the power thing over here, e to the power. So, if I now plot R t as a function of t, so this will be R 0 and it will be something like this. Right. So, this will be something like this, and the corresponding time constant, right. So, you fit it with e to the power minus t by tau r. So, you will get this orientational relaxation time. Okay, now, if you are interested on this anisotropy, that how easily the molecules actually reorient, then you can do this kind of prescription and you can get this tau r value. Now, as I told you that you can earlier during our discussion on TCSPC setup and the fluorescence upconversion setup, I told you that these in both the setup there are two components, optical elements was there, and I told you that I will explain those optical elements later on. And now this is the time to discuss about that. Okay. Now, consider that you have a setup and either TCSPC or upconversion, and you want to measure the lifetime. Right. So, what will be your way to do that? Either you will excite vertically and emission is collected vertically, or you excite vertically, emission is horizontal, or you excite vertically and the emission is unpolarized, right. You do not select, you do not put the analyzer. So, let me write this. So, for lifetime measurement, I could have three different situations. Like here I want to measure tau f, not tau r, right. Please note that. So, the three cases, case 1 I have vertical excitation and vertical emission. This is nothing but I parallel T, I already showed you, right. I can have vertical excitation, horizontal emission. Case 3 I can have vertical excitation and unpolarized emission. In the first case you already have seen. What is the first case? This is nothing but I parallel T. So, I can simply write the expression of I parallel T over here for the case 1. For the second one, this is nothing but I perpendicular T. So, let me write the expression, and for the third one I have not derived, but it can be derived without any problem, and let me also write that expression, right. So, here this is nothing but I parallel T, which is equal to I 0 by 3 e to the power minus t by tau f to 1 plus 2 r 0 e to the power minus t by tau r. this one is nothing but I perpendicular t. So, this is I 0 by 3 e to the power minus t by tau f to 1 minus r 0 e to the power minus t by tau r, and this is for the unpolarized. So, I do not write I parallel or perpendicular, I just write I t. This will going to be equal to some constant will be there, then I 0 by 3 e to the power minus t by tau f into 2 plus r 0 e to the power minus t by tau r. Now, you see in all these three cases, right, these three cases are possible case. So, in all these three cases, what you can see is that you wanted to measure the tau f, but you end up with the measurement of such kind of complex. See here tau f is present, here you have this tau f, here you have this tau r, here you have this tau f, here you have the tau r, and here also this tau f and this tau r. But you wanted to measure only the tau f, end up with measuring a mixture of tau f and tau r, and you will never get the fluorescence lifetime, that is defined as the tau f. But what is the prescription now for the measurement of fluorescence lifetime alone? So, that we are going to discuss now. Now, let me consider that these two this is my I perpendicular and this is my I parallel, right. I can consider it like that way, right here, and better I write the electric field instead of intensity, which is the square of this intensity electric field. So, I write this E parallel equal to square root of I parallel and E perpendicular is equal to square root of I perpendicular. So, right now what we are doing in other cases, either I was measuring this I parallel t or I was measuring this I perpendicular t or I was measuring everything, right, that was the thing what I said. But is it possible that I measure something between I parallel and I perpendicular? Why not? Because you remember that when I used my, let us say this is my sample cell and you are exciting your sample like this way and emission is getting collected at the right angle and you had your polarizer over here. Now, when the polarizer is oriented like this way, I assume that this is I parallel. When I rotate this polarizer like this way, this is I perpendicular, right, this is I parallel because this is like this and this is I perpendicular, and if I rotate the polarizer like this way, then it will make some angle theta, is not parallel not perpendicular. So, it is will make some angle, let us say theta, from the vertical excitation, right, from the parallel component. So, from here if this is this axis, then this may be theta, right. That is what I will going to draw over here. So, now if you collect the emission, then this emission will be collected at that particular angle theta. So, that is what I am going to write. Let us assume that you put your that analyzer in such a way that the light having such kind of polarization is only passing through, right, this analyzer. So, let me extend it over here. So, this is the position of my analyzer, this analyzer orientation. And I said that this is oriented at an angle theta from the parallel component. Now, I can simply do some trigonometry over here. So, the component of E parallel which will projected on this angle theta, I can calculate it. I will just draw a normal over here, right. If this is E parallel, then this will be E parallel cos theta. So, this will be my E parallel cosine theta, and if this is E perpendicular, then I will normal. So, then this part, so from here to here, this part will be E perpendicular sin theta. So, let me and this is right. Now, my life is simple, let me write it. So, I just simply write over here, if it is E parallel sin theta, that means the intensity is the square of that. When it is E parallel cos theta, then its intensity is just square of that. So, now I can write it like this way. You see, I is a function of t, right. No, I is not only function of t, it is also a function of theta now. So, here I is a function of theta and t is equal to I parallel t cosine square theta plus I perpendicular t sin square theta. So, now I will put the expression for this I parallel t and I perpendicular t into it, and then I will try to simplify this equation and let us see what happens, right. So, now I will put this expression. First one is I 0 by 3 e to the power minus t by tau f to 1 plus 2 r 0 e to the power minus t by tau r multiplied by cosine square theta, and I 0 by 3 e to the power minus t by tau f, here 1 minus r 0 e to the power minus t by tau r to sin square theta. This will be equal to I 0 by 3 e to the power minus t by tau f. I will take this common and then I will write it once again. So, this will be cosine square theta plus twice r 0 e to the power minus t by tau r cos square theta plus sin square theta, and then it will come as a minus r 0 e to the power minus t by tau r and sin square theta. So, I can rewrite this as I 0 by 3 e to the power minus, this is important, very important thing I am doing now. So, into here you see cos square theta plus sin square theta. So, I have 1 plus, and let me take this here r 0 this part, right. So, then let me write this r 0 e to the power minus t by tau r, right, and then this will be 2 cosine square theta minus sin square theta. So, 2 cosine square theta minus sin square theta. This means, okay, I am almost done. So, I 0 by 3 e to the power minus t by tau f, I will keep this part as it is, r 0 e to the power minus t by tau r, and this can be written as 3 cosine square theta minus 1. I am done. Now, you see, for a certain value of theta, this 3 cosine square theta minus 1 this value could be 0, right. If so, what will happen? This is 0. Okay, let me write for 3 cosine square theta equal to 1, right. I can write here cos theta is equal to root over 1 upon 3. Then when the value of 3 cos square theta is equal to 1, then this will be 1 minus 1, this will be 1 minus 1, then this quantity will going to be 0, then this whole quantity will be 0. So, what I will get? I will get this equal to I 0 by 3 e to the power minus t by tau f. See, for a particular value of theta, when cos theta equal to root over 1 by 3, that means theta equal to 54.75 degree. When theta equal to 54.75 degree, that means if the analyzer is placed at an angle 54.75 degree from the direction of excitation or from the I parallel, like this. This is I parallel, this is I perpendicular, like this. So, in that case, what you will going to get is that this term, this part vanishes, and what you will left over with this I 0 by 3 e to the power minus t by tau f. That means, you will be able to measure the lifetime, otherwise not. You can do another thing. If you just simply take I parallel plus 2 I perpendicular, let me write here I, suppose you have collected the fluorescent transient or fluorescence decay I parallel and I perpendicular, and then you do this one I parallel plus twice I perpendicular. Just put all these values, I mean that expression of I parallel and I perpendicular, and simplify it. You will also get that only tau f term is there. In this case, you have to measure 2 times at in the magic angle, and if you put this angle during measurement, then you have to measure only single time. Result is same, right? And this angle is a special angle, and this angle is known as magic angle. So, now you understand the role of those things I have drawn in TCSPC setup and up conversion setup. Those are the polarizer or analyzer. You have to set the analyzer at the magic angle, then only you will get the correct lifetime. Now, here one point I should tell you that suppose the lifetime, but sometime you will see that people are measuring without that magic angle polarization. That means everything is wrong, or under some condition that the lifetime measured without analyzer, without magic angle polarization is okay. It is okay only when the lifetime is very large compared to the rotational time, right. So, in case that tau r is much smaller than tau f, much smaller than tau f, then the decay of this part will not going to affect that way the tau f. But if you are interested in the time scale which is comparable with the tau r, then your decay will be distorted, right. For example, suppose you have a fluorophore whose lifetime is 1 microsecond. So, you are going to measure this decay from 0 microsecond to let us say you are going to measure like 5 microsecond, like if it is 1 microsecond. But the rotation of this fluorophore, right, is typically is in the order of tens of picosecond, 50 picosecond, 60 picosecond, 100 picosecond. So, the isotropic situation will be achieved in the solution within let us say 200 picosecond, but 200 picosecond is nothing in front of microsecond. So, the error will be very small. So, for those kind of long lifetime sample, you really do not have to worry about this magic angle polarization for the measurement of the fluorescent transient. But if you are in the domain of few tens of picosecond. It is must, right, otherwise all your data will be wrong. Okay, let us continue and we could see a nice equation now. What I will do now is the following. I will integrate it. What I will integrate? Integration 0 to infinity I parallel t dt. I will do that. I will do this integration. Let me write integration 0 to infinity. It is the form of I parallel t, I 0 by 3 e to the power minus t by tau f right. So, this integration 0 to infinity I parallel t dt, this is nothing but the steady state I parallel. So, I just termed it as I parallel steady state, right. So, it is integration over all the time. This I parallel t is changing with time, but this is just I have integrated it. So, if you evaluate this integral, what you will get? You will get such kind of form. Let me write without evaluating, which you can check later on if you want, otherwise take my word. I 0 by 3 tau f e to the power minus t by tau f, that limit 0 infinity minus 2 I 0 r 0 by 3 into 1 divided by 1 by, so it's little lengthy, plus 1 over tau r into e to the power minus 1 over tau f plus 1 over tau r, and here a limit is again 0 to infinity. So, if you put this value, this limit, so what you will get is I 0 by 3 into tau f plus twice r 0 divided by 1 over tau f plus 1 over tau r. So, you will get I parallel steady state as this. Now, similarly, I can also calculate this I perpendicular steady state. So, this I perpendicular steady state similarly, right, similarly we will do is you will get as I 0 by 3 to tau f minus r 0 divided by 1 over tau f plus 1 over tau r, and r, which is steady state, you can measure. I already told you how to measure it, this r, right, which is nothing but I parallel steady state minus I perpendicular steady state divided by I parallel steady state plus 2 I perpendicular steady state. And if you plug in the expression for I parallel and I perpendicular in this equation and simplify, you will be surprised to see that after simplification this result will be very simple, 1 plus tau f by tau r. Now, I can rearrange it and I can write it as r 0 by r s s is equal to 1 plus tau f by tau r. Very important equation. This equation is known as Perrin equation. And we will stop here today and we will continue our discussion on the next class. Thank you.